Okay, in this video we're going to be talking about the Navier-Stokes equation in detail and talking about what the physical meaning is behind each term. Okay, and so just as a reminder, so the Navier-Stokes equations are partial differential equations that express the conservation of mass and momentum in a fluid, and if you solve these you get the velocity and pressure distributions within that fluid, which are very, very valuable. Right? And so, you're probably going to be spending a lot of time solving the Navier-Stokes for certain situations, but I think just as important as knowing how to solve this is to understand what the physical meaning behind each of the terms is. And I think this is important to do whenever you have an equation in science and engineering, because it's a lot easier to remember an equation and to know what to do if you kind of physically understand everything about it. And so, so instead of relying on just straight up memorization, you have kind of a deeper conceptual understanding of kind of what you are doing with these equations. Okay? And that's especially important with Navier-Stokes because they are not easy equations to solve. And so, we have two um, differential equations here. I'm only showing one component for the momentum just for simplicity. And so trying to memorize this is very difficult unless you've been studying fluid mechanics for over 10 years like I have. Okay? Okay, so let's go over the continuity equation first. And so this is conservation of mass. All right, so this is kind of the easier of the two equations. And so if you know a bit about vector calculus, what you will see is that this equation expresses that the divergence of the velocity field must equal 0 in order for conservation of mass to be satisfied. And so what that basically means is that there can't be any spontaneous sinks or sources within the fluid flow. And so when you have a flowing fluid, you can't spontaneously have mass just kind of show up out of nowhere from like a portal from the nether dimension or something like that, right? Visually, what this means is that you can't have flow that kind of pushes in, kind of converges onto a point, or pushes out from a single point. Um, and so, it's kind of a more complicated way to, I think, explain something you may already know, that, you can't create or destroy mass, even in a flowing fluid, okay? But I do want to note that the form of the equation that I have here only applies to incompressible fluids, okay? And so if you have a compressible fluid where the density is a function of pressure, or it can change, then the continuity equation takes a different form. But that's usually a bit beyond the scope of an introductory fluids class. And so, but I did want to make that note here. Okay, so now let's talk about the momentum equation. And so this is kind of the big boy of of Navier-Stokes. Okay, so there's a lot of terms here, but if you kind of group them together into similar groups, it becomes, I think, a lot more easy to understand what they are and how to work with it. Okay, so let's start with the simplest term. And so we have partial u, partial t. And so this is simply our unsteady term. And so if you compare this to all the other terms in the equation, this is the only one that has a time derivative. And so what this represents is the fact that the velocity can change at a fixed location if the flow field is unsteady. Okay. But oftentimes in our analysis, we're going to set this term equal to 0 because we're going to make a steady state assumption. All right, next we have this group of terms, and so all of these guys go together, and these are what's called the convective terms. And so what these represent is the fact that a flowing fluid velocity can also carry momentum along with it. And so, this is, I think, the term that's most difficult to explain, but I like to think of it like this. And so if you have a flowing liquid, and so let's say you have a river, if you put like a twig in the river, intuitively we know that the twig will be carried along with the flow down the stream. Okay. And so basically what that means is that whenever you have a flowing fluid, it's going to carry stuff along with it. One of the things that it also carries is momentum. And so it's kind of this kind of almost paradoxical line of thinking that, the fluid can carry its own momentum, but the momentum is what's carrying the momentum down the stream. It's a little hard to wrap your mind around, but if you kind of say it a few times, it makes a bit more sense. Okay. But in actuality, these terms are very, very difficult to deal with, and in fact, we call these nonlinear terms because they're basically the product of a velocity times a velocity. And so, when we're trying to solve the Navier-Stokes equations by hand, usually we're doing everything that we can in terms of assumptions to get rid of these terms because these are not easy terms to solve. Okay. All right, next we have the pressure gradient term. And so this is the only term in the equation that has pressure, which is capital P, okay? And so the term in front, the one over rho, that's density. So don't confuse rho and P, right? And so what this term represents is the fact that you can have pressure gradients or differences in pressure drive a flow forward. And so if you think of flow in a pipe, um, flow always goes from high pressure to low pressure. That's how that kind of manifests itself in this equation. Okay, so that's that's very important for, say, pipe flows, but also atmospheric flows as well. Right, next we have the gravity term, and so this term represents the fact that flow can also be driven by gravity, right? And so fluid has mass, and as long as it has mass and it's sitting on Earth, there's going to be a gravitational pull, and so if the fluid can fall vertically, then it's going to flow in that direction, and so that's what this term here represents. Okay. And finally, we have this group of terms down here, and so this is the only terms in the equation that have the viscosity. Right? And so it's a little bit hard to tell, but this symbol right here is new. It's not the same as V, although in Greek letters they look almost identical. And so this term right here is the kinematic viscosity, right? And so this is where our viscous effects come into play, right? And so what they represent is the fact that viscous shear stresses have an impact on how the velocity is distributed in a flowing fluid. Okay. And so we'll get into this more as we solve equations in a later video. Okay, but one thing I want you to know here is that because we have second order derivatives here, when you actually solve for the solutions, these actually have a smoothing or a diffusive effect on the velocity distributions. And so because viscosity is present, you don't see very sharp changes in velocity in your flow. Okay? And so that's the introduction to Navier-Stokes. And so that concludes this video.